All right, let's get started. So today what we're going to do is, for the first part of class, just go through some questions from previous exams that cover some of the topics that we've touched on this semester. This class will focus only on multiple choice questions. In the next class, we will do some of the harder free response ones, just so you get a rough idea of like what kind of reasoning you're expected to be able to perform on the exam. Some logistic stuff, so your proposals are due today, so hopefully you've been working on those. We will try and get you feedback in the next week or two for each group. There is no class on Wednesday because I will be traveling, and there's no class on next Monday because of fall break. So our next class will be Wednesday of next week. And on that class, we will be doing some more practice for the exam and also talking about scaling laws for large language models. And then the following Monday will be your exam. Okay, any questions about the plan? Okay, so I wanted to focus mainly on these multiple choice exams because your exam will look pretty similar to these multiple choice sections. And I wanted to start with some of the questions on this exam. So unfortunately, I couldn't find the one without the answer, so I'm going to scroll very slowly here. Okay, so in this question, let me see if I can remove these thumbnails. All right. In this question, we are training a language model on a data set that has a vocab of 100,000 word types. And the problem says the perplexity of this model on the validation set is 30. Which of these statements is true about that result? So if we read through these choices here, we first of all know intuitively that perplexity represents how many choices the model, how many plausible words the model is choosing between at any given point. And so if you look at choice B here, it says it expresses the model's uncertainty over predicting the next word, and specifically the model thinks it could choose between 30 equally likely next words in this data set on average. The incorrect choices here are, your model almost perfectly predicts the next word. This is clearly not true if the perplexity is 30. If my model actually did predict the next word perfectly, what would its perplexity be? Any ideas? 1, right? There's only one choice that the model is choosing between. So this is certainly untrue. The high perplexity indicates that your model has overfit to the training data. So this statement is wrong in many different ways. First of all, if your model has overfit to the training data, the perplexity should be very, very low on the training data, right? So a high perplexity. Secondly, this is the validation set perplexity, so it says nothing about the training set at all. So this statement is wrong in many ways. And then this one was the most common wrong answer chosen. On average, your model has a 30% chance of correctly predicting the next word on the validation set. This is just not the right interpretation of perplexity. Okay, so you can expect, perhaps multiple questions about perplexity and language model evaluation, relationship between perplexity and probability, all of these kinds of things. All right, so this one, we're not going to really have any questions about fine-tuning on this exam because we are going to do post-training after the exam. So don't worry about this. However, I think most of you could correctly answer this question based on what you discussed in the class. We have not talked about nucleus sampling, so don't worry about that, or these things. So this problem, how many of you have started the homework? Wow, okay. I guess you do have your proposals. But you should expect some questions like this that are things that you should know if you completed the homework properly. So in this particular problem, it says we want to train a language model with a batch size of 16 in PyTorch. Which of the following locations of the optimizer.zeroGrad call in the training loop will prevent correct training? So this is something that you will have to do in homework 1, is write a training loop for your transformer encoder. And you need to call this zeroGrad function after either every batch or every example, depending on how you're implementing your training code. The reason is if you don't call this function, the optimizer will keep the gradients that are computed for previous examples and accumulate the gradients with new examples that you show it, which is not what you want to do. You want to compute a new gradient every time you update your model. And so you will, when you all start homework 1, have to make these decisions on what is the correct ordering of, when I compute my loss, when I do backprop, when I actually adjust my parameters with the step function, and when do I zero out my gradients. But even if you haven't started the homework, you should be able to reason through this question. So if we zero out our gradients immediately before forward propagation, that does really nothing because we're going to do forward and then back prop, and then we'll have our gradients and we can do our step. If we zero out our gradients after forward propagation, this also does nothing because we haven't done back prop yet to even compute the gradients. If we zero out our gradients after doing back propagation, which is what this loss.backward does, but before we actually take a step, now this actually has an effect on what our model is doing, right? Because here we've computed the gradient, now we're zeroing it out, and then we're going to take a step, which is nothing because we actually have no gradient to even take a step with. If you call it after doing the step, it doesn't affect anything because you've already adjusted your parameters. So this question is kind of representative of more coding related ones that you may see on the exam, where you don't necessarily have to memorize anything or write any code yourself, but you should be familiar with all of the functions used in homework 1 to create the transformer, self-attention layer, and the training loop of the transformer. Yes?
Will you release the solution to homework 1 before the exam?
Yes, the reference answer will be available as soon as a deadline hits. That's a good point. If I don't do that, please remind me on Piazza. Other questions about this? All right, so let's continue slowly scrolling down here. Okay, so this exam, by the way, was a take-home exam. So the questions that you'll see that are free response are generally much harder than what you would actually see in your exam because you don't have access to the internet or AI, and you have a limited amount of time to complete this exam. That said, we will go over some of these questions in the next class period because while they may be difficult in terms of you're not going to see things like this on your exam, you will see similar concepts popping up. So it's important to be aware of that. I do want to switch over to this exam, which I actually gave last semester. Some of you took this exam in my seminar last class, which was all multiple choice, but also has several questions that are directly relevant to this class. So I wanted to go over them. And we can start with, I think this one actually doesn't have solutions, so I can scroll faster. So here we have this question. In the transformer, what is the main intuition of using multi-head self-attention instead of a single head? So this is a fairly straightforward question, right? It does not do anything to the time complexity, right? We're not making it cheaper, certainly, by adding multiple heads. There's nothing forcing each attention head to focus on specific parts of the sequence, right? We never talked about any sort of constraint on what each head can look at. You could add such a constraint if you wanted to, but the default transformer self-attention mechanism does not have any sort of constraint. So each head can look at whatever it wants. It addresses the vanishing gradient problem. This is also untrue. We discussed residual connections as being one way to help the vanishing gradient problem in deep networks, but that's not what multi-head attention is doing. Finally, the correct answer is it allows a model to capture different types of relationships between tokens, right? So again, we talked about how this is simply an intuition, but we don't really have good ways to inspect the model to conclude that this property is exactly what this attention head focuses on and nothing else. Again, the question is asking just about the intuition, not about what actually happens. Okay, I see no questions on YouTube, so let's continue. Question 2, also very relevant to this class. Oh, yes.
So for previous question, but didn't you say that these multi-heads could, like, I don't know, focus on position or activate on certain phrases? So
Yeah, so the multiple heads could certainly focus on different things, but importantly, we are not forcing any specific head to do a particular task. Yeah, so that's all of the head-specific behavior is learned via backprop. Yeah. Okay, so let's move on to the second question here, where we're talking about element-wise addition as a composition function. So remember, we talked about many different composition functions. We started with element-wise addition. We moved to concatenation. Then we talked about recurrent neural networks, and then finally we got all the way to transformers. So this element-wise addition means we take all the word embeddings in our input sequence and we simply add them together, right? And then we can feed that sum, the vector sum, into a linear layer or into the softmax layer to predict the next word. So here, the choices are, first, it computes the same representation for every permutation of the input sequence. So this is the correct answer, right? This is the main problem with simply adding up all the vectors, is that we can change up the order of the sequence and the sum will remain the same. And so we're lacking information about the order. So note also, more relevant to the topic of our lecture today, that if we compute self-attention on a sequence of vectors, of word embeddings, that self-attention is also, it will give you the same representation regardless of what position or permutation, the ordering of the vectors is, which is why we need to add some sort of positional information into those vectors. We'll talk about some caveats to that at the very end of this lecture, but yeah, this choice A here is basically the problem with summing. So element-wise addition does not scale quadratically with the sequence length, right? You're simply just adding up all the vectors in the sequence. There's no computation of dot products between each word and every other word or things like that. So it's not like self-attention in that way. It does not introduce actually any nonlinear transformations if you simply sum something up. And there are no extra parameters, right? In naive element-wise addition, you are just adding things to get one vector that's passed into the softmax layer. So These two questions were pretty straightforward, but it's instructive to look at the wrong answers because get a sense of what obstacles you might encounter when answering these questions. Okay, so question 3 will be relevant to your exam, but we haven't covered this topic yet, so go back and study it after the next lecture. We will not be covering flash attention right now. And we're not talking about long context language models, so ignore anything like that. So the next relevant thing, okay, so question 9, you will be able to answer after today's lecture, but not right now, unfortunately. Question 10, so you should expect multiple questions about tokenization. The tokenization we had a whole lecture on, and there's many different variants of it. It has a big impact on language model performance. Maybe we can all do this problem together instead of me just telling you the answer. So the question is, which one of the following statements is true about subword tokenization in LLMs? So choice A, subword tokenization can yield many different tokenizations of the same input sequence. Choice B, the vocab size of LLMs using subword tokenization is smaller than that of byte-level models. Choice 3, no state-of-the-art closed LLMs use subword tokenization. And choice D, subword tokenization follows predefined linguistic rules to split words into subwords. Okay, so how many of you think the correct answer is choice A? All right, what about choice B? What about choice C? What about choice D? All right, so about like 5 people raise their hands. This is a tricky topic. The answer is actually choice A, and we did briefly talk about this in our tokenization lecture. So remember that in subword tokenization, when we're doing something like BPE, we always start with the either basic bytes or the characters in our vocabulary, right? And then we iteratively kind of merge pairs of these types and add the most frequent pair to our vocab, retokenize, and do this for some number of steps. So at the end of the day, I have a setting where my vocabulary might contain bytes, characters, subwords, and full words, right? So if I have a sequence like my favorite LLM is Quen, I could tokenize this into perhaps 5 words, like my favorite LLM is Quen, or I could tokenize it in a character sequence, like MY space FABORITE, right? All of these different tokenizations and mixes of these are viable sequences in a subword tokenizer, which begs a question. If I want to compute the probability of a sequence, and I'm using like a vocab and a tokenizer that I obtain through a process like BPE, how do I actually compute the probability of that sequence? Because there's many different valid tokenizations of that sequence under my BPE segmenter and vocab. And the correct answer is, if you really want the exact property, it's kind of intractable because you have to sum over all possible tokenizations of that sequence in order to get the probability. In practice, no one does this. They measure the probability of the shortest possible sequence that you can make with that tokenizer, because our goal is to reduce the sequence length, right? And so in BPE, if I could tokenize my sequence into 5 words versus 100 characters, my tokenizer will default to the 5-word choice. That said, unfortunately, there is still some non-zero probability put on each of the other alternative tokenization. Yes?
So the other, like your height, if you have a word, and the word is in the BP's
Yeah.
thing set, it could still like choose a different way to do it.
So remember that we are going to, like the algorithm will choose the segmentation that has the fewest tokens.
Okay.
However, there are other valid segmentations.
Okay, so that's
Yeah.
what this is. Not.
Yes,
The
that's right.
The one that just uses each individual
Yeah.
letter is still valid.
Yes.
Okay.
Other questions about this? Okay, so there have been several papers written about this phenomenon and like how much does it actually affect the performance of these language models? Answer is seems like not too much, and obviously everyone loves these kind of subword tokenizers. OpenAI, Claude, Gemini are all using some form of subword tokenization, but still something that you should keep in mind as a possibility. Okay, let's go down to okay, this one is question 14, also relevant. So you can ignore this like long context papers part, but the question is, why is self-attention problematic for long inputs? And so here we have choice A, self-attention cannot model any dependencies beyond a short fixed window of tokens. Is this true? No, right? There's no theoretical limitation on the number of tokens beyond which self-attention just fails, right? It can scale to any window size. Self-attention scales quadratically with the sequence length in both time and memory. Is this true? Yes, it is true. We discussed why this is, right? We had the example of sequence length of 2 versus a sequence length of 4 versus a sequence length of 8, and you can draw out the attention matrix to see the computation increasing quadratically. The softmax function in the self-attention mechanism, okay, this choice doesn't make any sense, so we're not going to discuss it. Self-attention requires more heads for longer context than shorter ones. Intuitively, you might think, well, that makes sense, but there's no like hard rule that something requires more heads, right? It's always an empirical question. You can compute your performance of your language model on different tasks and see if it benefits from having more heads or more layers or more heads and more layers or whatever. So the only thing that's true here is B. All right. What else can we do here? Okay, so question 19 you will be able to answer after our scaling laws discussion. We can do question 21. It is kind of intuitive, although it'll be more clear after today's lecture. So here it says we train a language model using learned additive position embedding. So these are the position embeddings that we've been talking about up till this point in the semester, where for each input word embedding, we simply add a learned position embedding that corresponds to a single particular position. So I have a different embedding for position 1, different embedding for position 2, and so on. So the question is, what happens if at test time we feed in a sequence that is longer than the maximum training length? So generally when we're doing pre-training, we have to select a maximum sequence length, and that is generally based on our hardware restrictions, right? Like we know self-attention scales quadratically in the sequence length, and so we can't just train our model on arbitrarily long sequences. It depends on our GPUs and things like that. Also depends on how large our model is, right? If we have a huge, deep model with many different heads, then we, for the same amount of compute, probably won't be able to fit as many tokens as a much smaller model with fewer heads. So we have to set a maximum sequence length during training, and this question is asking what happens if at test time we receive an input sequence that's longer than everything we've trained on. So if you think about it, if we have a position embedding for position 1, 2, 3, all the way up to our maximum sequence length during training, at test time I receive a longer sequence. I don't actually have any position embeddings for the tokens that are beyond the maximum sequence length. And so any naive implementation will simply return an error for these kinds of sequences because it doesn't actually have parameters to add to the word embeddings to get this position information in. And so all of these first three choices are, they could happen if you had a better way of handling the maximum sequence length being exceeded at test time, but any normal implementation will simply return an error because there are no position embeddings for those later tokens. And so this is actually a focus of our lecture today is how do we get around this kind of naive limitation? Are there more clever methods that don't involve just having a specific embedding for each position? All right, so question 22 is also about byte level tokenization. So here we are asking, what is the main drawback of byte level tokenization? So we talked about this toward the end of the previous lecture, right? So if we're doing byte level tokenization, we have some advantages in terms of, well, we can potentially handle every type of language. All of the Unicode characters could be encoded in our sequence. So do we have a reduced ability to process out of vocabulary words? In fact, one of the advantages of byte level tokenization is that you can better handle out of vocabulary words, right? Larger vocabulary size, not really true, right? I could have like a 256 item vocabulary if I used byte level tokenization with no BPE or anything on top of it. So not really something to worry about. Increased sequence length. This is a big problem with byte tokenization, right? Like I might have a sequence that's 5 words long and transformed into something that's like hundreds of bytes long. That's egregious, but yeah, you get my point. Like the sequences get very long and your compute goes up. We know self-attention scales quadratically. So this is going to limit our maximum sequence length during training time. Reduced ability to memorize factual knowledge, that is just a random statement, completely unclear if byte level models have any issues with this compared to subword or word level tokenization. All right, so this one, also a good question. When training a language model, how do we compute the loss over an input batch? So we've talked about this many different times. Choice A, compute the average negative log likelihood over all tokens in the batch. This is the correct answer, right? And we can get the perplexity by simply exponentiating this quantity here. We do not compute the maximum negative log likelihood. We do not compute the squared loss either when we're doing training of language models. The square loss was used in that example to demonstrate how backprop works, and it's generally used in regression problems. But for language modeling, we're treating it as a large classification problem, right? And so we're using the cross entropy loss to predict the next word. All right. Let's see. Okay, so this kind of question you should also expect. Like, what happens to the perplexity if X, Y, Z is true about my language model? So here, and maybe we can do this one together as well, you are evaluating the test perplexity of a vanilla bigram language model. The test set contains a bigram that never occurred in the training set. Which of the following accurately describes what you would expect to see in this situation? So A, the test perplexity is unaffected by the unseen bigram. B, the test perplexity is undefined due to the unseen bigram. C, the test perplexity increases only slightly because there are many more observed bigrams than unseen ones. D, the test perplexity decreases slightly because the probability of the unseen bigram is 0. So how many of you think the correct answer is A? What about B? What about C? And what about D? All right, so I think a majority of you were for choice B, which is correct. This is a big problem with n-gram models, is if you have a bigram or an n-gram at test time that you did not observe at training time, if you look at the count for that bigram in your table, it's going to be 0, right? And when we're taking the product of all of these conditional probabilities in an n-gram model, that means your whole sequence probability is going to be 0, aka your whole test set's probability is going to be 0, and you can plug that into your perplexity calculation to figure out that that is just going to lead to an undefined output for the perplexity. This is why, if you're using n-gram models, you probably want to do what is called smoothing to add some non-zero probability to any unobserved n-gram that was unobserved at training time. But in our semester, in our kind of notes, we said that this is also a reason why we may want to shift over to neural language models, right? Because we're not going to get this issue if we don't observe a two-word sequence. We still have the embeddings for each of those individual words, and we still have a composition function that can compute some vector, the representation of that prefix. And so it's one of the advantages of neural models versus these count-based ones. Okay, so highly recommend you, make sure to understand the math here. This also involves conversion from probability to like log probability to perplexity. So just make sure you're okay with all of those concepts. All right. What else can we? Okay, so we will talk about this NOPE paper at the end here. So you can come back to this one. I think okay, so question 34. What is the primary role of residual connections in transformer language models? We talked about this as a way to alleviate the vanishing gradient problem and help the optimization of the transformer to let the gradient have kind of a shortcut when it gets to each transformer block. So because you're directly adding the hidden state of the current layer to the input of that layer, the gradient has two paths that it flows down instead of one. And the shortcut path does not involve a lot of different matrix vector products like you do when you follow the path down the actual transformer block. And so this helps the optimization a lot. None of the other choices here make sense, but they all seem like slightly plausible, so yeah. All right. So which of the following statements is true about hidden states in transformer language models? A, the hidden state at each time step is a nonlinear function of the previous hidden state and the current time step's input. Is this true? No, right? Because here in a transformer, the hidden state has no dependency on the previous time step's hidden state, right? That's what happens in a recurrent model. Transformer gets rid of this so that we can parallelize all the computations. B, the hidden state at each time step is a function of only the current time step's input and includes no information about previous tokens in the sequence. Is this true? No, right? If this were true, transformer would be a really bad model, right? Because it only, each hidden state has only information about the current word. We know the whole point is to figure out like which words are most relevant for the current prediction and kind of upweight them in the current token's hidden state. C, the hidden state at each time step can be computed independently of hidden states at the previous time steps. True, right? This is the whole motivation of the transformer. And yeah, we can skip over whatever random statement. This is adding up the value vectors associated with current and previous time step. This is not true, right? We're using the attention scores to weight the value vectors. All right. I think there should be... Yeah, so those are all the relevant questions for this exam. There's many other previous exams as well. If you find a question and you're not sure if we covered any of those topics, or there are some terms that you don't understand, it's likely we just didn't cover whatever that is. But if you have any questions, you can post them on Piazza, and we will clarify if you need to understand that question or not. Okay, so any questions about anything that we just covered here? Okay, so now let's turn to our topic for today, and we'll see how much we can get through, and then we'll resume on next Wednesday, so a while from now. You all get a break from me. I get a break from you too. All right. So we're going to be talking about positional encodings. So note that here I'm not saying embeddings, and that's because the methods that are used to integrate position into today's language models actually don't involve embeddings. They involve rotations or otherwise manipulating the query key dot product in order to inject position information directly into that. But let's start with the basics. So self-attention is not inherently position aware. And so what we have been talking about is this setup where we might have these vectors for favorite LM is, and before we put this into our transformer, we said we would add these position embeddings, so P1, P2, P3, and then these were our C1, C2, C3. Then all of this goes into our transformer. And so we should first discuss exactly what this approach is doing. So first of all, it is injecting absolute position info. And this means that I have some information about the exact position that a particular word is at. So if my word was at position 529, I would have a different embedding for 529 than 528, than 2, than 7, and so on. So I have some information about the absolute position of that word in the sequence. The other thing is that these are additive embeddings. And so this means that I'm adding new parameters that are associated with position. And these parameters actually have to be trained via backprop, just like my word embeddings and every other parameter in the network. We already talked about this with regard to the practice question on the previous exam, but one big drawback about this method is that it does not generalize to longer sequences at test time, right? And so, because I just don't have a learned embedding for a position that I haven't seen at test time. So the terminology we're going to use here is that it has or lacks position extrapolation. This means cannot generalize to positions, or sorry, I could say sequences that are longer than the maximum training length. And we, again, talked about this when we were doing those exam problems, that we have to choose a maximum sequence length during pre-training based on our compute resources and things like that. And so if I train my model with a max sequence length of 512, I'm not going to be able to use the model if it's using these absolute additive position embeddings with a test time of length 1024. So this is a big problem. Ideally, I would want a way to inject position information in such a way that regardless of how long the sequence is at test time, my model is able to kind of deal with that sequence length and understand all the relevant information within. If you actually read the Transformer paper, how many of you actually opened that PDF and at least read a few words from it? Okay, so roughly half the class. You will note that that paper has a different kind of position embedding, which doesn't involve any learned parameters. So they use what's called sinusoidal position embeddings. They do still add them to the input word embeddings before passing everything into the transformer. But they say that this kind of position embedding has better extrapolation than learned additive position embeddings. However, a lot of studies since then have showed that those position embeddings actually aren't that good at extrapolation, and no one really uses them anymore. These absolute learned embeddings were very popular during the era of BERT. So basically all of the BERT type models used the most simple form of position embedding. But it is this lack of ability to generalize is the biggest flaw in this setup. Any questions about this? Okay, so let's move on then to a different type of position embedding, which is relative position embeddings. So it's kind of rare that you have a task where the absolute position of a word is super important, right? Like knowing that the word favorite occurred at position 13 instead of 15 makes a huge difference in terms of like either predicting the next word or solving some real world task, right? In general, what we might care about more is the relative distance between two tokens in the sequence, right? Like in attention, I might have some sort of bias that tokens that are closer to each other should have higher attention score than tokens that are further apart. Maybe not for every head, but in general, I probably want this ability to, at least decide, should I focus on tokens that are close to my current position or far away from my current position, or things like that. I should remove M's here. So let's, just to have an example of this, let's take a look at two different sequences. So here I might have the sequence, my favorite LLM is Quen. And I might have another sequence, I don't know, like honestly, comma, my favorite LLM is Quen. So here, if I label the positions, I'll just start with index of 1, 4, 5, and now I have 1, 2, 3, 4, 5, 6, 7. And so in both of these sequences, let's say I'm computing self-attention at the last token here. So I'm looking at the dot product between this quen query vector and all of the key vectors in the sequence. Is it really a big deal that I should have a different attention score for LLM in this top sequence than in the bottom sequence? Because note that LLM is at position 3 and quen is at position 5 in the top sequence, and LLM is at position 5 and quen is at position 7 in the second sequence. So if I'm using absolute position embeddings, the attention scores between quen and LLM are going to be different in both of these sequences. However, I should maybe prefer that those attention scores should be the same, because quen and LLM are both like 2 positions away from each other in both of these sequences, right? And really nothing has changed dramatically about the new information that has been inserted. So I might want to, instead of having absolute position information, encode relative position information. The problem is it's not really clear on the surface how to inject relative position information into our attention computation. Absolute position is very easy. We can just add something to each position in the sequence. But relative position changes for each token in the sequence, right? So I wanted to show an example with very intuitive relative position embedding. Sorry, I should stop saying embedding. Relative position encoding method called alibi that is quite intuitive to understand. So here, we're going to remove the position embeddings completely. So we're not going to add anything to the input word embeddings. And we're going to compute our self-attention as normal. Note that here we're not, so I'll write this out explicitly, no position embeddings added to input C sub I, the word embeddings. So we're going to just compute our query key dot products like before. So we are going to compute all of these for a 4-word sequence, and we're going to mask all of these red ones. So this dot product, this matrix of dot products right now has no information about position at all, right? I have simply computed this QK dot product without any sort of position embeddings being added. So what they do in this alibi method is, after you compute these QK dot products, you add a simple linear bias to this matrix. So that looks like this. We're doing element-wise addition with a matrix of the same dimensionality, so a 4 by 4 matrix. And it's going to be 0 on the diagonal, which indicates that here there's no difference between the position of the query and position of the key, right? So this diagonal, I'm computing q1.k1, q2.k2, q3.k3, q4.k4. And then every offset of these is going to be marked by a negative number. So here I have q2 and k1, right? So I'm computing the dot product between query vectored position 2 and the key vectored position 1. And so there's a difference of 1, and so I'm going to have a -1 negative bias in this slot. Similarly here, it's Q3 and K2, Q4 and Q3. Now, at this cell here, I have Q3.K1, so there's a difference of 2, and so I'm going to have a linear, like a further negative bias here to indicate that, okay, these two vectors are further apart than all of the other ones. And I can, have a -3 when I'm doing Q4 and K1. So you might be thinking, okay, well, I'm just like adding negative numbers to this QK dot product matrix. How do I know if those are even the right scale or anything like that? How do I, manage the impact of this additive bias? What they do in Alibi is they simply multiply this bias matrix with a scalar m that's between 0 and 1. And so let me write that down here. M is a hyperparameter. It basically acts as the slope of this change here. And so if m is really small, then I'm not really impacting my attention scores too much. But if m is large, then this attention score is impacted quite a bit. And the idea is that each head can have a different value of m. So maybe some heads are more sensitive to position than others. Again, m is a hyperparameter, so it does add a lot more hyperparameters to your model in terms of for every head you may have to decide, okay, what value of m should I use for this particular head? They provide some easy choices that you can use that seem to improve performance. One thing to note here is that there are no additional parameters in this alibi method, right? So I added one hyperparameter for each head, which is this m slope value, but there's nothing that's being trained here, right? I have a fixed bias matrix with these negative numbers that I'm going to use for every head. I'm not learning any embeddings for position at all, so no extra parameters to train. And the results of this method show much better extrapolation to sequences longer than max training length. And so this is partly because there are no added parameters here. So the model can't like overfit to the positions that it's observed during training. And simply adding this this bias matrix. And so if I observe a sequence that's longer than my max training length, I can still construct a bias matrix like this and use it to change the dot products to represent that. So it's not perfect. The extrapolation ability kind of runs out after you get to about twice the training sequence length. But it's still a lot better than the learned additive embeddings for which you have no extrapolation ability at all. Yes?
Can you explain the M and also what you said about like it can only extrapolate to twice of the embedding?
So I'll answer the second part first. Why can it only extrapolate to twice the sequence length? This is an empirical finding. So they did a bunch of experiments and they found that their perplexity kept reducing as they added more tokens past the training sequence length, but after some point they stopped seeing any increases. There's no theoretical reason why that is. It's just what they found. So the M is, so let's say I set M to 0.01. That means what I'm adding here, this -1 here would become something like -0.01. So it's a very minor effect. If I set M to 1, however, then I'm going to actually affect this dot product by a lot more. I could set M to something even larger potentially and have a huge impact on this. So it just controls how much position information is going to affect the dot products.
So if it's a low number, it means that the positions don't matter. But if it's a high number, it means that the positions matter.
Yeah, well, I would say if it's a low number, then this head is not particularly sensitive to position compared to, yeah. So by setting different heads to different values of M, you can have some heads that are more position invariant and others that are more sensitive to position. Yes.
So what exactly does like subtracting the numbers from the dot products do?
Yeah, so you can think about it as, okay, so let's say this Q4.K1 had a very high dot product. So, I mean, here it's hard to like discuss the magnitude of the dot product, but let's say this dot product was like 2.1 in this cell here. Now, if I have this additive negative bias here, let's just say M is 1, now my dot product becomes minus, like 0.9 or something like that. So now I had a positive dot product that indicated that this key was very relevant to this particular query. However, because of the position bias, it may no longer be relevant when you consider all of the other keys. And actually, after you compute the softmax, the probability of this may be very low, if that makes sense. So depending on the value of M, you can have a larger or smaller impact on the probabilities after the softmax. Yes?
Do we have any other matrix for the positions besides just having zeros, -1, -2, minus?
You could, yeah, so the question is, can I choose a different bias matrix instead of this one? Yeah, you could. This linear one is very simple, and that's why the paper authors tried this, because why would you do something complicated if this simple thing works? But yeah, there have been some variants of this that try with more different matrices, but the idea is still kind of the same. Yeah. Yes.
So, can the n value be negative?
Sorry.
Can the n value be negative and the whole matrix can be negative?
Oh, can the M value be negative? Well, then you would be upweighting things that are farther away from the current position, right? So I don't think that happens in practice because that's generally not helpful for language modeling. But yeah, in theory you could do it. I don't know what it would do to training, but yeah.
The main solution is to take the negative values.
The main solution is?
It's always important to take the negative values for all of
Yeah, that's right. And then you just adjust the magnitude through this M hyperparameter. Okay, let me check on, oh God. I hope I don't have a bunch of questions. I read the Transformer paper. Good job. It's honestly a tough read, especially now, but good job for attempting it. Okay, so the next thing we're going to talk about in the brief time that we have left, so maybe we won't go into too much detail, is the method that's actually commonly used for today's language models. This method is called ROPE. So this is stands for rotary position encoding. And I believe this was developed by people at Microsoft a few years ago. So the general idea is, kind of similar to what we did in Alibi, where we want to be able to capture these relative, distances between queries and keys. But we may not want to just, as many of you were saying, why are we choosing this particular bias matrix? And do we really want to be adding something to our dot products every time? Do we also want some sense of absolute and relative position embeddings? So if we just look at a 2D visualization of our query and key vectors, so let's say they're in 2D here. And we can go back to the example from before. So let's say I'm interested in the dot product between the query vector for Quen and the key vector for favorite. So let's say that when Quen is at the first, sorry, what position is? Okay, so Quen is at the, so this is Quen at position 5. Now, the general idea of rope is that instead of adding any information to the embeddings directly, or adding some bias term into the after you compute the QK dot products, in rope we're actually going to rotate the query vectors and the key vectors before computing the dot product. And that rotation, the angle of the rotation, is going to be defined by the relative distance between these two words. So that's the general idea. So in this visualization, I might have Quen, the query vector at position 5, Quen at position 6, and Quen at position 7. And here, like for each position, the subsequent position that I might have this word, I will rotate this vector by some hyperparameter theta. So if theta is small, then my Quen vector will rotate very slightly as the position changes. If theta is large, I might have like many rounds of this, so the query vector is very sensitive. So this is kind of analogous to that M hyperparameter in alibi. We have some hyperparameter that's controlling how sensitive this encoding is to position. And now, let's say I have my key vector for, what was I doing? Favorite, I think. So this might be the key vector for favorite at position 2. This might be the key vector for favorite at position 3, and so on. And so here, when this changes, I'm also going to rotate it by some value theta. And so the general idea is that no matter where in the sequence these two words are, Quen and favorite, let's say that Quen is at position 5 and so here, and favorite is at position 2. So the dot product between this query and key here, dot product between, I'll just write Quen 5 and favorite 2, should be the same as the dot product between, say, Quen 6 and favorite 3. Quen 6 dot favorite 3. So we want a setup like this where we apply some transformation to the queries and keys such that this is true. The dot product, right? We're computing the query and key dot product. This dot product should be the same if the relative distance between those two tokens is the same, regardless of if the absolute position of those words has changed. So that's the general idea behind rope. So now if you've taken a linear algebra class or any sort of computer vision class, you probably have encountered this rotation matrix, right? If we have a vector and we want to rotate it, how do we do so? So I'll just write it out here. You don't need to know these details for the exam or anything like that, but it will be good to have some intuition of how this method works compared to things like alibi and learned embeddings. So we're going to multiply by a rotation matrix. And these rotation matrices are designed with some identities in mind. But the way it works is we have this rotation matrix where we have some hyperparameter theta. Again, that's controlling the sensitivity of the, the rotation to the position. And we have this p, which is the index of the particular word in the sequence, the position. And so if I want to rotate some input vector at position P by this theta, I can set up a rotation matrix that looks like this. So cosine P theta minus sine P theta, sine P theta, and cosine P theta. And so I can take my query vector, I can multiply it by a rotation matrix, I can take my key vector, and I can multiply it by the corresponding rotation matrix. And now I have this property of rotation matrices of composition. So if I have two different vectors and I rotate them both by different angles, and then I take the dot product of those two vectors, it's the same as if I, well, let me just write it out and then it'll become more clear. So I'm getting too abstract here. So this is the rotation frequency. This is the position in the sequence. And so the question is, how do we integrate rotation into self-attention? And so in rope, we're going to rotate both the query vector and the key vector. So let's say I had Q of Quen, and let's say Quen appeared at position 5. So I'm going to use my rotation matrix, P equals 5, times this WQ, this is our projection, and then times C of Quen, the word embedding associated with Quen. So in normal self-attention, I don't have this rotation, right? I just have WQ times the word embedding. But here, I'm going to rotate that resulting query vector by this, theta, where P times theta. So here, P is 5. So I'm going to rotate it up by 5. And so when I compute the key for favorite, I'm going to similarly take my rotation matrix and then apply it to this standard key vector. So in both cases here, in normal self-attention, I don't have this rotation matrix, but here I'm doing this rotation after I compute the query and key vector. Yes?
Why did we cross out the rotation?
I was just indicating that these are not, so I'm going to erase them now, but these are not things that we do in normal self-attention. Okay. So the only thing we're adding here is the rotation of the query and key. So now, remember that what we want to compute is the query vector of Quen dot the key vector of favorite. And when we're doing this, in general, we're going to have this transpose, but I will just omit that for clarity. But we want to compute this dot product between query vector of Quen and the key vector for favorite. And the important thing here is due to the rotation matrix properties. So the way we set up this matrix up here, this is actually equal to WQ times C Quen. So this is our normal query vector times this rotation of 5 minus 2. So we actually have this relative distance that is encoded via these properties of the rotation matrix times our normal key vector, WK times C favorite. And so you can see that the way that we set this up, we have no information about the absolute position. This depends only on the relative position, aka the difference in the positions between the query vector and the key vector. And so to summarize here, we're going to have the same dot product regardless of absolute position, as long as P quen minus P favorite is the same. So if I do it this way, in my example up here, my dot product for quen and favorite in the first sequence is going to be identical to the dot product between quen and favorite in the second sentence, because this final equation here only depends on the relative difference in positions. And so this example here was only in 2 dimensions. In practice, of course, your embeddings are much larger than 2 dimensions, right? They might be 100 or 500 dimensions. And so you can check out the rope paper for how they scale this up to larger dimensions. But as some intuition, if I have, let's say, like a 100-dimensional query vector here, we're basically going to split this vector into segments of 2 and apply different rotations to each of these. So this could be theta 1, this could be theta 2, this could be theta 3, this could be theta 4, and so on. Each theta is a constant that controls the rotation frequency. So again, it's very similar to the M in alibi. If I set theta to something very small, then my QK dot product is going to be relatively unaffected by position. If I set it to be something very large, then I'm going to make big changes to the dot product if the relative position difference is high. And so this may be for particular features that are more sensitive to position. So by mixing up all of these, I can get a balance of more position invariant and position specific features. Yes?
Why by 2?
I mean, it kind of follows the intuition here, right? Like, we can apply this specific rotation matrix to any 2-dimensional vector. And so they just generalize this to the multi-dimensional case by using exactly this equation. If you look at the rope paper, they just have a big block matrix where they repeat this for each kind of segment of 2 dimensions of the input. Yes?
So we're only caring about towards position, relative positions. But let's say like there was another word like before them that.
Yeah, that's a good question. So here I've only described how this works for 2 specific words. But note that here, and this is a very important point, for every word in the sequence, I'm going to rotate it by an angle that is specific to the absolute position of that word in the sequence. So for example, if quen is in the 7th position, I'm going to, this will be like cosine 7 theta, sine, negative sine 7 theta, and so on. The key thing is that all of the words are rotated by this angle depending on their absolute position. But then when I'm computing the QK dot product, those are only a function of the relative difference between each of the QK, not the absolute, due to this, property over here. So this is happening all in parallel to all of the words, and we have this nice property that we don't have to add this big bias matrix if we just rotate all of these in advance. Yeah. Yes?
If you think about the numerical terms of the data, what can be the minimum and maximum values?
The minimum and maximum values of? I mean, theta is an angle, right? So in this case, like if you were thinking about it in degrees, 0 to 360 degrees, right?
Is it related, we have to vary those vectors to find that?
So again, it's a hyperparameter, and generally they offer like some pre-selected thetas that work well, but you have to adjust these for longer context inputs and so on. Okay, so we're out of time. I will start with this on, whenever we have a class next, and then we'll talk about scaling laws, do more exam prep. Good luck with your proposals and homework in the meantime.
For our exam one, we will have only multiple choice.
Yes.
For the